what we discussed last time near the end, from what some students asked me, I realized I did not make something so clear. So today I want to make a few points. First, 上回我们在最后说是这个一个 U， 本来我们讨论的是说一个 one dimension 的 U。那么在这个我们在 talk about 一个 equilibrium point， 为什么这是 equilibrium？ 因为 derivative of U is force， equilibrium 就是没有 force， 所以是在这种地方。When it's near the bottom, it's a parabola. It's approximately a parabola. What we want to do is to have a many-dimensional problem. So think of this U as a U of x, y, z. So it's a surface. If it's a U of x, y, 是一个 this is U, this is x, this is y. It's a surface. At the surface there is a point which is a minimum, and we want to discuss what happens near the minimum. So suppose there are three variables x, y, z. Then we expand U as U0. That's the U, the potential energy at the point of equilibrium. Then we have the first order term, alpha x plus beta y plus gamma z. Then we have second order terms. We have cubic terms. If it is an equilibrium point, the derivative of U with respect to x, the derivative of U with respect to y, the derivative of U with respect to z, at x, y, z equal to 0, has to be 0. So if I take the derivative of this with respect to x, I get alpha. The derivative of these terms, when you put x, y, z equal to 0, all becomes 0. So that means that this term alpha has to be equal to 0. Beta has to be, so this has to be equal. This is called the first order term. The first order term must be 0 for the point to be an equilibrium point. These are called the second order terms. These are called third order terms. The second order terms and third order terms for small vibrations are all very small. For example, suppose x, y, z are all of the order of 1%. Then the quadratic term, what are the quadratic terms? That x squared, y squared, z squared, x, y, x, z, z, x. No, x or y, z. There are 6 quadratic terms. 假如 x, y, z 都是1%的样子，那这些 terms 都是1/1000的样子。那到这些呢是100,000,000,000的样子，所以这些都是 for small vibrations， 这些都可以 neglect。那么这些就是我们叫 concentrate， 这些是1/1000，这些是100,000,000,000，你可以先把100,000,000,000忘记掉，所以就只有这个。假如你是有不是3个 variables， 有 n 个 variables 呢，这就变成了 summation aij xi xj。所以 so what's the conclusion? The conclusion is that near an equilibrium point, for small vibrations, you can neglect high order terms and only include the quadratic terms. The linear terms are 0 because we are talking about the equilibrium point. Now once you have a quadratic expression like this, you can write it as this times A times this. A is a square matrix. Then you can diagonalize this by a theorem about the matrices. So after the diagonalization, so this is x, it becomes x prime times diagonal times x prime. In other words, it becomes equal to a constant, let's say, alpha 1 x1 prime squared plus alpha 2 x2 prime squared plus alpha n xm prime squared without cross terms， 没有 x1 prime x2 prime， 因为这是 diagonal。那你把这个跟这个 kinetic energy 加在一起的话，就变成了很多的 harmonic oscillator。Because harmonic oscillator 的 typical 的是它的 potential energy 是 x 一个 dimension 的 harmonic oscillator， 它的 potential energy 就是 x squared。那么现在这些都 separate， 所以就变成了好多 harmonic oscillator each with its own frequency. These are called the principal frequencies. In other words, so 我们可以把它写成一个 near equilibrium for small vibrations the motion is a superposition of many harmonic oscillators, of many harmonic motions. Each with a natural frequency. Let me read that. Near equilibrium for small vibrations, the motion is a superposition of many harmonic motions, each with a frequency. This is a very general statement. Next point. I went too fast last time at the end. We were discussing a forced oscillation. So it's mx double dot plus bx dot plus kx is equal to f cosine omega t. By the way, 假如是 omega， 它不是 omega t， 是 omega t plus phi。那我就把它写成 omega of t plus phi over omega。我把这个叫做 t prime， 那就变成 omega t prime。所以你要换成t prime 的话，这就没有 phi 了。换一句话说 ，you can always consider just to shift the time coordinates, take a different point as the origin, and use that as the new time. Then the differential equation does not have the phi, so we can always consider this equation. This equation let's 叫做 A， 然后我写了另外一个 equation 是这样的，这 equation 叫 B。 I did not make clear why I can go from A to B. Now I want to make that clear. Suppose you solve this equation. After you solve it, you take the real part of your solution x. Then this becomes you take the real part of this equation. The left side looks like this. The right side becomes this. So, any real solution, any complex solution of B has a real part which satisfies Therefore, this is a very common trick. Instead of dealing with this type of equation, A, you deal always with the type of equation B. Why is B better than A? Because exponential I omega t has the property that no matter how many times you differentiate it, it remains the same form, only multiplied by constant. So therefore, it's easy to solve. After you solve B, you take the real part, then you get a solution of A. So that's what I went through too fast. Third point. Last time we talked about the solution of A. Now let us write down the homogeneous equation. I call this C. This is called the homogeneous equation. Homogeneous meaning that there's no term not proportional to x or x dot or x dot double dot. Namely, there is no f term. Now, any solution of A plus any solution of C is still a solution of A. Does everybody agree? If I take a solution, any solution of A, add to it any solution of C, I now use that sum, and I want to prove that that sum satisfies this equation. Obviously, because when you take the left-hand side, suppose this one is called, the solution of this one is called x1. The solution of this is called x2. Now I take x1 plus x2. If you take x1 plus x2 and substitute on the left-hand side, the x2 part drops out because of this. So you only are left with x1, so you get a set equation of. So let me write it down. Any solution x1 of A plus any solution x2 of C is a solution of A. And that is called a general solution. So a general solution is always consists of an x1 plus an x2. But the x1 part we already discussed the last time is an exponential I omega t. When you take the real part, it becomes a cosine. It doesn't damp down. As t goes to infinity, x1 does not damp. Does not damp down， 就是不是慢慢的变低了。可是 x2 是一个 solution of C。我们上回已经 we talked about that it damps down with an exponential decrease of the amplitude. So therefore, x2 does damp down. Dig does not. Dig does. 所以 after a sufficient long time, there's only x1 left. So every time you turn a switch, all the electric connections form a network, and next semester you're going to learn that satisfies the equation exactly like this equation A. And when you turn a switch on, immediately the current flowing through it consists of two terms, x1 and x2. The x2 part is called transient. Transient 就是暂时的。That part will die down in time, and only the x1 part is left. And this is true of all vibrations. Section 17-3 is very interesting. I didn't know it. It tells you how it's going. How a shed measures distance. This must be a new discovery of the last 20 years. It shows how very advanced techniques are used by various animals and insects. Now in this chapter and the next chapter, 17 and 18, we're talking about waves. Waves are different from what we have been talking about, is that it's a function of two variables. It's not just a function of t, but it's a function of x and t. For example, a vibrating string. So every point here, this is called y. Every point here is moving up and down. So y is a function of both x and t. And if it's a drum, then the surface of the drum would be moving. So you would have z of x, y, t. A typical vibration is like this. Y is equal to y0 times sine or cosine of omega t plus phi. Y0 is called amplitude. This is called phase. Omega is called angular frequency. Sometimes called angular velocity. Sorry. Plus minus omega t. For a fixed t, it's a sinusoidal wave. Take a wave. What's the wavelength? wavelength is usually called the lambda. If you increase x by lambda, the phase should increase by 2 pi. That's the definition of a cycle. So k times lambda has to be equal to 2 pi. So lambda is related to k by 2 pi over t is called period. Period means for a fixed point. X is, so your fixed point, fix x. Then when t increases by capital T, by the period, it should increase by 2 pi. So omega times t is equal to 2 pi. So therefore t is equal to 2 pi over omega. One over t is the number of seconds, number of cycles per unit time. For example, suppose t is 1 over 1,000 of a second. Then in 1 second you can have 1,000 cycles. So 1 over t is called frequency. In the book it's called f. Usually in the physics literature, one does not use f, one uses nu, the Greek letter nu. But in the book, because nu looks very much like v, for reasons I did not understand, they chose a font, 一个字体，这个书上的字体 v 是跟 nu 一样，所以这个是书上就把这个 frequency 不用 nu， 它用了一个 f。不过通常在 physics literature 里头，这个 frequency 都是用 nu。Anyway, 我们 follow the book, so t is equal to 1 over f. 假如是个 f of kx minus omega t， 这随便是一个什么样子的 function？ 这是 x， 这是 y， 这是 f。 这是在 t 等于0的时候。现在 I increase t a little bit, then this point would move forward. So when t increases, the whole curve is moved to the right.这是在 t 等于0， 这是在 t 等于一个 delta t。 In other words， 这个整个的 wave 是向这面走。Now the f of kx minus omega t is a wave that moves to the right. F of kx plus omega t is a wave that moves to the left. Is that clear? Because f of 0， 先说在 t 等于0的时候，那么 f of 0是在 x 等于0的时候，你在 t 等于1的时候，你要是同样要 f0 的话，那你就得 put kx 减去 omega 等于0，那岂不是你就得出 x 是等于omega over k to the right with a velocity equal to omega over k. 这是 with velocity with speed omega over k. Speed 只是 absolute value， 所以现在有个重要的 formula， 就是 omega over k 是等于 speed。向左或者向右 depend on whether it's kx minus omega t or kx plus omega t. All these are elementary, but you have to go through this argument once. It's very simple. Notice that the shape of the wave is not changed. Either f of kx minus omega t or f kx plus omega t, they represent waves which move to the right or to the left without changing shape. No matter how originally it looks like, it doesn't change shape. Actually, if you watch a water wave in the ocean, the surface water wave does move. If the bottom is not sloped, if the bottom is fixed, then for a long stretch of distance, the wave moves without changing shape. The reason that you usually see 白浪 foams, that's because the bottom is sloping upwards, so that the water becomes shallower and shallower. When that is the case, you have the waves would change shape. Why does it change shape? It's actually very simple, because there's a drag of the water at the bottom, and as a consequence, the bottom moves too slow, the top moves too fast, so that it accumulates. So eventually it tops over. As a matter of fact, if the slope is very gentle, and if the speed is just right, 它要变成钱塘江潮，钱塘江的大潮，那是非常有名的事情。It's called there are a few places in the world where there is something like 钱塘江大潮, and in the 19th century, in people in the science of hydrodynamics, they understood this. So there are books and books written about how 钱塘江的大潮 was formed, and the fundamental point is that it has to be a gently sloping bottom. Now we are going to move on to a subject which is not discussed properly in the book， 就是比如说是一个钢琴的弦，就是刚才我画的图，这弦在振动的时候 ，it may look like this。It satisfies a certain equation. The book did not discuss this equation because the book avoided using differential calculus. Instead, the book gave a very tricky derivation of the velocity. I studied that derivation. It is essentially correct, but it's too tricky, and it's not the right way to teach that particular problem. So we are going to analyze this problem, and we look at the one particular. This is the string, this is the original position, and now we look at the segment of it. The string has a tension, which is tau. The string has a mu, which is equal to mass per length. So I'm now going to look at a small segment of it from x to x plus dx, x plus delta x. 那么 horizontal force on string at x这是一个负的 minus tau 是 the force times but not horizontal, vertical, sorry. Vertical force on the string at the point x 是equal to 负的 tau 乘上 sin theta。这个 curve 是这样。它的 slope 的 angle 我叫做 theta， t sin theta 是那个 force 的 vertical component。因为 because theta is small, we are talking about a small vibration. So sin theta is equal to tangent theta. Sin theta at the point x, tangent theta at the point x, which is equal to minus tau. What is the tangent theta? Tangent theta is the derivative dy dx at the point x. Vertical force on string at x plus delta x. 那就是在这一点。那 similarly 等于 the same expression 在 delta x plus delta x， 可是改了一个 sign， 因为这面是向上，那面是向下，所以 it's equal to plus tau dy dx at x plus delta x。 所以 total force, total vertical force on string in this interval就是这两个的 difference 是 equal to tau times dy dx x plus delta x minus dy dx x. Okay, let us plot. This is x. 我在这 plot dy dx. 方才有个 y as a function of x， 这是这个本来这个 string。那么它有个 derivative， 这个 derivative 是表示这样。所以我们现在要 take derivative 在这一点，减去 derivative 在这一点。那我 I claim 这是等于 tau 乘上 d square y dx square 在 x 乘上 delta x， 因为这个 difference 就是这 derivative 这个是这个 tangent 的 direction， 这个是这个角的 direction。 But when delta x is very small, these two are the same. So therefore, this in the limit 它变成这样。我们现在 neglect gravity。那我们现在用 Newton's law， mass 这个 string 在这里头，它的 per unit length 的 mass 是 mu， so the mu delta x 是等于 mass 乘上 acceleration d square y dx square dt square。这是 acceleration. Mass times acceleration should be equal to force. So we get finally或者写成这个叫做 wave equation. It's the most important equation. The book gave a tricky derivation of this velocity. I had never seen that the derivation before. I studied it. It's correct, but it's too tricky. It's not the right way to learn it. The right way to learn it is what I told you. This is the right way to derive this wave equation. this equation sometimes is written in a different way. One writes 1v squared. Sometimes one introduces notation. Differentiate with a t 就写一个小 subscript t， 两个 t 就是 second derivative with respect to time 等于 y xx。yxx 就是 second derivative of y with respect to x. ytt is second derivative of y with respect to t. These are different ways of writing the wave equation. This is a problem with two dimensions. One space x, one time t. You can write down wave equation in four dimensions. Wave equation in 3 + 1 dimension. 3 + 1 dimension means 3 space coordinate, 1 time coordinate. That's the real space, and that equation becomes 1/v² times ytt, not y, times let's say a field f, phi tt is equal to phi xx plus phi yy plus phi zz. That's the wave equation in 3 dimensions. Before 1865, there was the science of optics, 光学. There was, and it was already known, people had already measured the velocity of light, and it turns out to be approximately the value we have today, which is 3 × 10⁸ meters per second. In 1865, Maxwell wrote down Maxwell's 4 equations, or Maxwell's equations. He then manipulated with those equations, eventually found an equation like this, with a velocity which came from his equations. His equations were derived from electricity and magnetism. So the V that he calculated came from electrodynamics. He observed that velocity is approximately equal to the experimentally observed velocity of light. So in his paper he said he believes that the light is in fact an electromagnetic wave. And that was one of the great moments in the history of mankind, because after that one knows that there are electromagnetic waves, which was not known before, and that in fact optics or light waves are electromagnetic waves. And of course that discovery, that understanding in the 20th century gave rise to radio, to the internet, to all the communications that we use today. And furthermore, one understands that there are other types of waves. There are microwaves, there are ultraviolet waves, there are X-rays, there are gamma rays. All of them are electromagnetic waves, and they all satisfy fundamentally an equation like this. For example, if you have a drum,方才讲这个 drum 有 x, y, 它的 displacement 是 z of x y t， 它 satisfy the equation 就是1 over v squared z t t is equal to z x x plus z y y。一个 pipe， 不管是封着口的或者是散着口的，你在吹一个笛子的时候，它里头的这个 the air mass inside of it moves back and forth, and the density of air rho becomes a function of x and t. And that rho satisfies 1 over v squared rho tt is equal to rho xx. Okay, now let's try to solve this equation. Not in general, but we discuss what is called a standing wave.我们就 take 原来的 equation， 就是那 string。我们 assume 这个 y 是一个 product function， 是一个 a of x 乘上 b of t。它本来是一个 function of two variables， 我们 assume 它是一个 product of 两个 function，one of which depends only on x, the other depends only on t. Okay, let's substitute in here. We get 1 over v squared, the tt, so I get x times the second derivative of b with respect to t. That's the left hand side. The right hand side is the double derivative with respect to x and single without derivative. So we move everything that depends on t to one side. So we get b t divided b of t times 1 over v squared is 等于 a Now, this is a very peculiar equation. On the left side, you have a function of t. On the right side, you have a function of x. And it's supposed to be valid for all values of x and all values of t. So what's the conclusion?这个 equation 左边是一个 function of t， 右边是一个 function of x， and 随便你 x 改 t 改，这 equation 都对。Does anybody know how to conclude? 我 claim 这个东西必须要等于一个 constant。Independent of anything. 我为什么呢？我 fix 一个 t， 我改 x， 因为你 fix 了 t， 所以这东西都不能改，因为它右边不改。不对，如果我 fix 一个 t， 改 x， 你随便你怎么改 x 的话，还是那同一个 t， 所以它左边不改，所以右边也不能改。 所以代表右边 independent of x。就是 both sides must be the same constant because 你可以这样讲 this expression 用左边一看它是个 function of t that means it's independent of x 右边你看它是 independent of t 所以它既不 depend on x 又不 depend on t 所以它必须是 constant 所以这是一个 minus k square 为什么我写成 minus k square 而不是 plus k square 呢？这你1分钟以后就可以看出来，这个 plus k square 也可以，不过is of no interest to us。那我现在比如说是把右边的写的，你就都是 a double prime x 是等于 minus k squared a of x. That's our old friend. It's a harmonic motion. If it's a plus sign, it will become an exponential motion. We have also discussed that. And we don't want to have very large solutions. So we just take the minus one. So therefore we get a of x 是等于 a0 sine of kx plus 5. Similarly, the left side tells us b double x, b double t is equal to minus k squared v squared b of t, which we shall write as omega squared b of t, where we take omega equal to kv. 假如这是一个 plus， 假如 k square 前面是不是 negative 是 plus 的话，那么这里就变成 plus， 那就要变成 time derivative 就变成 exponential. Oh no, we don't discuss such. There are such solutions, but they are of no interest to us. So therefore, we get the B is a sinusoidal wave. So it's a product of a sinusoidal function with respect to x times a sinusoidal function with respect to t. 这就是一个 string. 那么我们先来 talk about the space dependence boundary condition. The x 等于如果是一个 string。 那么在 x 等于0，这点是 x 等于0，在 x 等于0的时候，它是拴住了，所以 y 是等于0。在 x 等于 l 的时候 ，y 也等于0，这是这 boundary condition。你把这 boundary condition 提到这上去，那这 phi 就得等于0，所以 a of x 就等于 a0。 Sine of kx such that x 等于0是它等于0，而 kl sine of kl 就等于0，所以 kl 等于 n pi， n 等于1、2、3。 n 等于1的时候，这 solution 是 sine of pi over Lx。所以在 x 等于0的时候它是0，在 x 等于 L 的时候它是 pi， 所以就是这样一个。n 等于2的时候呢 ，ax 是等于 a0 sin of 2 pi over L x。那么 x 等于 L 的时候，它等于2 pi sin of 2 pi， 所以呢是这样。n 等于3的时候呢 ，L of x x 等于 L 的时候，它是等于3 pi。在这情形之下 ，lambda 等于什么？我们有 formula for lambda。lambda 等于2 pi over k。所以是等于2 pi 等于 2L over n。这是17:52。所以这地方 lambda 等于 2L， 这地方 lambda 等于 L， 这地方 lambda 等于 2L over 3。Do you agree？ 这是等于 2L。Because 这只是半个 wave， 所以它的整个一个 wave 是 2L， 整个一个 wave 就要有上面还加上底下，所以这是 2L。这个情形之下呢，这就是一个 wave， 所以 lambda 就等于 L。这个情形之下呢，你这样是一个 wave， 这有个半，所以 L 的时候是一个半，所以是。所以从这到这儿是一个 wavelength， 那当然是2/3 L。刚才我只 talk about A， 还得要乘上 B， 乘上 B 就再乘上一个sinusoidal wave， 可是的 whole thing 一块乘上sinusoidal wave， 所以如果 A 是这样的话，你再乘上那 frequency 就大家一块，所以比如说是那个 B 那部分等于正一的时候是这样， B 那部分等于负一的时候就是这样。所以它就在这里头，每一点就是在这儿动。So if you， 假如这是一个 string， 它在振动的时候，你看起来的话，因为它动得很快，你就只看见这两个边，你就看见是这样一个。在这个情形之下呢，就变成是这样。这种地方叫做一个 node。就是那个 vibration 等于0的地方叫做个 node， 所以在这个情形之下两边是 node， 在这个情形中间还有个 node， 在更加一个 n 的时候就有两个 node 在中间 etc。 而这个 frequency 呢是等于mv over 2l。v 是等于 square root tau over mu， 我们已经有那一equation。这个是17线。If you look at the piano, for every key of the piano there is a string, and the different strings are of different lengths and of different tension. They are adjusted such that the fundamental frequency is equal to the frequency you want for that key. When you strike a key, all of these vibrations, what we found is one solution. Say for n equal to 1. You can also have a solution for n equal to 2. But any linear superposition, the equation is linear. The wave equation is linear. So if you have one solution of the wave equation, if you have another solution of the wave equation, if you add the two, it's still a solution. So that means you can have the different frequencies all occurring at the same time. So when you strike a key, the C key of the piano, you get the fundamental frequency, but you also get higher frequencies. The higher frequencies are the multiples of that frequency according to this formula. But what determines the ratio of the different frequencies? That is determined in a very complicated manner. It depends on how you strike it. It depends on where you strike it, how you strike it. So it is a complicated. For example, if I strike it at this point, at a node, then it's not likely that it will excite this mode. So the ratio of the different frequencies, the different frequencies are in integral ratios of each other according to this formula. But it depends on where you strike it. There are different ratios of the amplitudes. And in general, and also it depends on whether you strike it just at one instant of time or it's a somewhat longer time. 一个 piano 里它 strike 的时候是一个东西上头有一些绒布， so it's a very complicated thing, and one doesn't do any computations about it. One just listens to it, and one adjusts it such that it's the most pleasing sound. But in general, when you strike one key, it's usually the fundamental frequency. That means the n equal to 1 frequency that's been used. Now, if you have a violin or you have a huqin, then in a violin or in a huqin, you change L because one hand moves and changes the L. One end of the string is fixed. The other end is fixed, but you use your hand to create a new boundary condition. So L is changing. By changing L, the frequencies depend on L according to our formula. So therefore, by putting your finger at the different positions, you create different frequencies of sound, and the multiple of the different ends again depends on how you strike it. 那你用一个弦 the way the 弦 where you put the 弦 etc etc or create different qualities of sound. Now, I want to prove a fundamental statement. A standing wave is a sum of two traveling waves. You could sine kx cosine omega t, for example. We all know this is equal to 1/2 of sine kx minus omega t plus sine of kx plus omega t. This is a simple trigonometric formula. This is a vibration that we have been talking about. It's a standing wave. Standing wave because it's like this. It's a fixed. It's the same shape, only the amplitude is vibrating with the time. That's called a standing wave. But if you write it in this fashion, this is a wave that moves to the right. This is a wave that moves to the left. So a standing wave is actually a sum of two traveling waves. It has to be this way because any solution of the wave equation is always a sum of a standing wave plus it's always a sum of two traveling waves in opposite directions. Because the sum of a traveling wave this way plus a traveling wave this way is a general solution. Any solution of the equation is a sum of two such traveling waves. So this is not a surprise. So we now know in some sense the physics of a stream vibration. But what we discussed is a case where the boundary condition is that the y is equal to 0 on this end and y is equal to 0 on this end. There are other boundary conditions. First case, at x equal to 0, we have y equal to 0. At x equal to L, we have y equal to 0. That's the case that we talked about. A second case is y equal to 0 at one end, and dy dx is equal to 0 at the other end. The second呢是 dy dx 在一面等于0 dy dx 在另外一面也等于0。How do we make this? You make this in a string like this. At this end, it's fixed. At the other end, you allow it to move, but you make its derivative fixed. So you can do you can have something like this, which can move. So it can be like this. The best thing is a pipe. A pipe with one end fixed, the other end open. Because if the pipe is open at one end, then the air there can freely move. If the air can freely move, it means its density is fixed. That means d density dx is equal to 0. So that's this equation. So an open pipe satisfies this. If it's open on both ends, that's this one. So this is a fixed string on both ends. This is a pipe with one end closed, one end open. This is a pipe with all three, with both ends open. So we have possibilities of all three kinds. You can read the section 18-6. Let us go through the case of case 3. Pipe open at both ends. The equation is the same. 1 over v squared y tt equal to y xx. We again write y as ax times dt. We again get one over v squared b double t is equal to a double x is equal to minus k squared. So a double x is equal to minus k squared a of x, and a of x is a sinusoidal wave. A sinusoidal wave, you can always either write it as a sine or as a cosine, but we shall write it as a we want dy dx equal to 0 at both ends, so it's better to write cosine. So I write as a0. Cosine kx, when you differentiate, becomes minus sine kx. When x equal to 0 is 0. So it's easier to choose. You can choose anything, but you have to follow through the rules. And it turns out if you choose cosine, it's the results in the calculation are much simpler. And the boundary this satisfies a prime of 0 is equal to 0. The other end is a prime of d a dx. When you differentiate y, you only differentiate a. So dA dx at x equal to L has to be equal to 0. That's the other boundary condition. That means A0 minus A0 K sine of KL is equal to 0. So KL is equal to m pi. That means K is equal to m pi over L. N is equal to 1, 2, lambda is equal to 2 pi over K is equal to 2L over N. The frequency is equal to NV over 2L. So let's take n equal to 1. N equal to 1, K is equal to pi over L. So A is equal to cosine K pi over L. It's like this. N is equal to 1. So A is equal to A0 cosine of pi over L x. N equal to 2. A is equal to A0 cosine 2 pi over Lx. In this case, lambda is equal to 2L. In this case, lambda is equal to L. N equal to 3. A is equal to A0 cosine 3 pi over L. So 它要到3 pi。3 pi 是什么意思呢？是everybody happy? I think, in fact, you have all had this in high school. The only thing that you didn't have is the wave equation. Now we have today derived the wave equation and solved the equation for the standing wave case. So that's the difference between what you are learning now and what you have already learned in high school. And I'm sure the 3 boundary conditions you are also very aware of. The only thing different is that you learn the origin of it starting from the wave equation. Now let us discuss a problem of chapter 17. problem 51p. The problem 是一个 string， 可是这 string 有点奇怪。It consists of two different material. The total length is L. 可是 part of it is of one material, part of it is of another material. Tau is of course fixed. The tension is fixed.可是呢，它有两个 mu， 一个 mu1 and mu2， 在这儿是 mu1， 在这儿是 mu2。Let's investigate what happens. The differential equation that we have remains the same. So we still have mu d squared y dt squared is equal to tau d squared y dt squared. So I still have the same equation. But v 现在是一个不是一个 constant， v 等于一个 function of x， 在这一段的 v 是一个 value， 在这段的 v 是另外一个 value。v 等于 v1 for x less than L1， v 等于 v2 for x大于 L1。So the equation is the same, only the v is dependent on x. So we still do the same thing. We write y is equal to a of x, b of t. And we still have the same equation, which is a double x v squared of x divided by a of x is equal to b divided by t times bt. This is the same as before. The only thing is that v now depends on x. Again, the left side does not depend on t, so the whole thing doesn't depend on t. The right side does not depend on x, so the whole thing doesn't depend on x. So the whole thing doesn't depend on either x or t, so it's equal to a constant. So it's equal to minus. Omega is a fixed number. In other words, omega is not a function of x. So we have d double t equal to minus omega square bt. That means b is harmonic. B is sinusoidal. In t. So 它是一个 harmonic motion. 所以这个 string 你如果 strike 的话，它变不出吸气的，它的那个 the sound depends only on the frequency. So therefore it's like an ordinary string. The quality may be different because the proportion of different harmonics, n equal to 1, n equal to n equal to 3, might the proportion might depend on this joint of two materials. But the A equation becomes now more complicated, because we now have A double x is equal to minus omega squared over v squared, which is a function of x, times A of x. Or we write it as x is equal to minus k 1 squared A of x for x less than L1, A double x equal to minus k2 squared A of x for x greater L1. So in each region we have a sinusoidal wave, but the k, that means the wavelengths are different. So for x less than L1 and x greater than L1, we have in each a sinusoidal wave, but with different case. That is to say, with different wavelengths. So now we have to match them. This is a typical type of problem. We have to match these two waves at x1. We have to match these two waves at the x and L1. What is meant by that? That means that 第一个 region 的 y 在 x1 地方就等于第二个 region 的 y， 第一个 region 的 derivative of y. In other words, y is continuous at x equal to L1, and dy dx is continuous at x equal to L1. Digital matching. Okay, I think we better do this next time. This gets a little bit complicated. After we match, we'll find the complete solution. The complete solution, however, also the amplitude of the two sides have to be matched. And if you have a uniform string, then the vibration and amplitude at every point is given by that A. But now you have two different amplitudes for the two different regions. They are each sinusoidal, but they may not be the same. And also there is a phase difference. So this is a little bit complicated. We'll do that next time. We'll finish this discussion next time.